Imagine the sound of the universe itself ringing like a bell, deep, resonant, almost haunting. That's what scientists heard for the very first time in 2015, when gravitational waves from two black holes colliding over 1 billion light-years away finally reached Earth. It wasn't just a whisper from the cosmos. It was a roar, a confirmation of something Albert Einstein predicted a century earlier, proof that space and time could ripple like the surface of a pond disturbed by a stone. And that sound, that was the beginning of a revolution in how we understand the universe. Gravitational waves are more than just cosmic vibrations. They're the fingerprints of the most violent, awe-inspiring events in existence: black holes merging, neutron stars spinning into oblivion, even echoes from the birth of the universe itself. For decades, they were just a theory, a mathematical quirk in Einstein's equations. But now, thanks to some of the most sensitive instruments ever built, we're not just theorizing about them. We're listening to them, and what they're telling us is rewriting the textbooks. This isn't just science, it's a whole new way of seeing the cosmos. Think about it, for all of human history, we've explored the universe with light, peering through telescopes to study stars and galaxies. But light can be blocked, distorted, or lost in the void. Gravitational waves, they pass through everything, carrying secrets from the darkest, most distant corners of space. They're like a cosmic telegraph, transmitting messages we're only just beginning to decode. And in this video, we're diving into 30 of the most groundbreaking discoveries these waves have revealed, from the bizarre behavior of black holes to clues about the very fabric of reality. Buckle up, the universe is about to get a lot stranger. The moment it happened, the world of physics changed forever. On September 14, 2015, at exactly 9:50 in the morning Universal Time, a ripple in spacetime, a gravitational wave stretched and squeezed the Earth itself as it passed through. It lasted less than 0.2 of a second, but in that fraction of a heartbeat, the Laser Interferometer Gravitational Wave Observatory, or LIGO, captured something extraordinary. The signal, named GW150914, was the sound of two black holes colliding over 1.3 billion light-years away. One was 29 times the mass of our Sun, the other 36. And when they merged, they formed a single, spinning black hole 62 times heavier than the Sun. In that cosmic collision, 3 times the mass of our Sun vanished, not as light or heat, but as pure energy, vibrating the fabric of the universe itself. LIGO didn't just hear this event, it proved Einstein right in the most spectacular way possible. Back in 1915, his theory of general relativity predicted that massive objects like black holes would warp spacetime, sending out waves when they moved, but even Einstein doubted we'd ever detect them. The distortions were just too tiny. Imagine trying to measure a change in distance thinner than a human hair across the entire span of our solar system. That's the precision LIGO achieved. Its twin detectors, separated by nearly 2,000 miles, use lasers bouncing through 4-kilometer-long vacuum tubes to catch these spacetime shudders. When the wave passed, one arm of the L-shaped instrument stretched by an almost unfathomable 1,000th the width of a proton, and yet that was enough. The implications monumental. Before GW150914, black holes were mostly theoretical objects we inferred from their gravitational pull on stars or the X-rays they emitted. But this was direct proof, two black holes spiraling into each other, warping spacetime as they merged. It wasn't just a discovery, it was the birth of an entirely new field. Gravitational wave astronomy lets us hear the universe in ways light-based telescopes never could. Suddenly, we had a front-row seat to the most violent, invisible events in the cosmos, events that don't glow, don't shine, but shake the very structure of reality. And this was just the beginning. What LIGO detected that morning wasn't a cosmic rarity, it was a glimpse into a hidden universe teeming with black holes dancing in the dark. Within months of that first detection, scientists realized something astonishing. Binary black hole mergers, once thought to be exotic rarities, happen far more often than anyone predicted. Gravitational waves revealed that across the vastness of space, black holes are constantly pairing up, tangoing in tight orbits, and colliding with enough force to momentarily outshine every star in the observable universe combined. Take GW 1509114's successors, events like GW 170804, where two black holes 50 and 34 times the Sun's mass merged 700 million light-years away. Or GW 190521, a bizarre merger involving one black hole spinning so fast it nearly tore spacetime itself. Each collision follows a similar script. Two black holes, locked in a death spiral by gravity, whip around each other hundreds of times per second before merging in a millisecond burst of energy. But here's the twist. The sheer variety of these mergers defies expectations. Some involve black holes too massive to form from collapsing stars, suggesting they might be the products of earlier mergers. Others spin backward or at odd angles, clues to chaotic origins in dense star clusters where gravitational tugs shuffle black holes like cosmic dice. What's truly mind-blowing is how often this happens. Since that first detection, LIGO and its European counterpart, Virgo, have catalogued over 90 confirmed mergers, roughly one every month. Extrapolate that across the cosmos, and you're looking at thousands of these events happening somewhere in the universe every single day. Each collision leaves behind a fingerprint, the new black hole's mass, its spin, even the direction it's hurtling through space. Together, they paint a picture of a universe where black holes aren't just lurking in isolation, they're social creatures, constantly pairing up, colliding, and growing. Perhaps most tantalizing is what these mergers reveal about the fabric of spacetime itself. When black holes collide, they don't just make waves, they ring spacetime like a bell, and the tone of that ring depends on the black hole's properties. Scientists can analyze these tones to test Einstein's theories under extreme conditions. So far, general relativity holds up perfectly. But with every new detection, we edge closer to finding cracks in the theory, potential signs of new physics. These mergers also solve cosmic mysteries. Some of the detected black holes are too heavy to form from a single dying star, suggesting they're second-generation black holes, the products of earlier mergers. Others move at odd angles, hinting at violent origins in star clusters where gravitational interactions kick them into unlikely partnerships. It's like piecing together a cosmic family tree, where every collision reshapes our understanding of how black holes are born, live, and die. And the discoveries keep coming. In 2019, LIGO and Virgo spotted GW 190521, a merger that produced the first clear evidence of an intermediate mass black hole, a long-theorized missing link between small stellar black holes and the supermassive giants at galaxy centers. This one weighed in at 142 solar masses, a Goldilocks-sized object that could explain how the universe builds its most colossal black holes. Every ripple tells a story. Some whisper of ancient stars collapsing in solitude, others scream of chaotic dances in crowded stellar neighborhoods. Together, they're rewriting the rules of black hole astronomy, proving that the universe's darkest objects are far more dynamic, far more social, and far more violent than we ever imagined. And with upgraded detectors coming online, we're about to hear the cosmos louder than ever before. But the universe had another surprise up its sleeve, one that didn't just shake spacetime but lit up the sky. On August 17, 2017, gravitational waves rippled through LIGO and Virgo detectors. But this time, something was different. The signal, named GW 170817, lasted nearly 100 seconds, far longer than the brief blips of colliding black holes. And within moments of the detection, telescopes around the world swiveled toward a faint galaxy 130 million light-years away. There, in the constellation Hydra, two neutron stars, city-sized remnants of dead stars, each more massive than our Sun, had spiraled into each other in a cataclysm so violent it forged gold, platinum, and other heavy elements in its wake. For the first time in history, humanity didn't just hear the cosmos, we saw it too. This was multi-messenger astronomy in action. Unlike black hole mergers, neutron-star collisions don't just produce gravitational waves, they erupt with light across the entire electromagnetic spectrum. Gamma-ray telescopes caught the first flicker just 1.7 seconds after the gravitational wave arrived. A short, intense burst of gamma rays, the birth cry of a newborn black hole or hypermassive neutron star. Over the next hours and days, observatories from radio to X-ray wavelengths tracked the aftermath, a rapidly fading blue glow called a kilonova, caused by radioactive debris expanding at nearly light speed. That glow contained fingerprints of freshly minted elements, solving a decades-old mystery. Where do heavy elements like gold, platinum, and uranium come from? Now we know they're forged in the furnaces of neutron star collisions, scattered across the cosmos like cosmic seeds. The data was staggering. The merger ejected material moving at 30% the speed of light, creating shockwaves that glowed for weeks. Spectra revealed telltale signatures of strontium and other heavy metals, confirming theories that neutron star smash-ups are the universe's primary factories for elements heavier than iron. Even more astonishing, the event produced an estimated 10,000 times the mass of the Earth in gold alone, enough to coat every planet in the Milky Way in a layer of precious metal. GW 170817 didn't just answer old questions, it opened new ones. The gamma-ray burst was weaker than expected, suggesting these cosmic fireworks might come in different flavors. The afterglow's shape hinted at a structured jet of material punching through surrounding debris, a detail that could explain why some bursts are visible from certain angles and not others. And the neutron stars themselves, each about 1.4 times the Sun's mass, challenged assumptions about how such dense objects behave under extreme conditions. But perhaps the most profound revelation was how perfectly gravitational waves and light complemented each other. By combining the two, scientists measured the expansion rate of the universe with unprecedented precision, a figure called the Hubble constant. Gravitational waves revealed the system's distance, light revealed its host galaxy's velocity. The result, a tug of war between competing methods to measure cosmic expansion, deepening one of cosmology's biggest mysteries. This collision was a Rosetta Stone for the cosmos. It proved that gravitational waves and light travel at the same speed, a key prediction of general relativity. It confirmed that neutron star mergers create both short gamma-ray bursts and kilonovae, and it showed that the heaviest elements aren't just stardust, they're the ashes of stellar corpses colliding in the dark. Since GW 170817, astronomers have raced to catch more of these cosmic symphonies. Every neutron star merger is a chance to study matter at its most extreme densities, so high that atoms collapse into seas of quarks, magnetic fields trillions of times stronger than Earth. Some might even produce magnetas, neutron stars with magnetic fields so intense they warp spacetime itself. The message is clear: the universe doesn't reveal its secrets through just one window. By listening to spacetime and watching the skies, we're piecing together a story written not just in light, but in the very fabric of reality. And with every new detection, the chorus grows louder. That distinctive chirp, a rising crescendo ending in a sudden silence, isn't just a sound. It's a cosmic fingerprint, a coded message from the violent dance of massive objects millions or even billions of light years away. When LIGO scientists first heard it in 2015, they weren't just listening to noise. They were decoding the final moments of two black holes spiraling toward collision, each oscillation in the signal revealing secrets about their masses, their speeds, even the fabric of spacetime itself. Picture this: as two black holes orbit each other, they lose energy in the form of gravitational waves, causing their orbits to tighten and their speeds to increase. The frequency of those waves rises as the objects get closer, creating that telltale upward sweep in pitch, the chirp. The faster the pitch rises, the more massive the objects. The louder the signal, the closer they are, and that final, abrupt cutoff, that's the moment of merger when the two become one and the ringing of the new black hole takes over. It's like listening to a cosmic sonar, where every wobble and warble in the signal translates to a physical detail about the collision. But the chirp isn't just a simple tone. It's packed with harmonics, subtle overtones that reveal the black hole's spins. If one or both are rotating rapidly, they drag spacetime around them like a whirlpool, imprinting a distinctive twist on the waveform. The exact shape of the chirp also tests Einstein's general relativity with unmatched precision. Any deviation from the predicted pattern could hint at new physics, extra dimensions, modifications to gravity, or even exotic objects like wormholes. Perhaps most astonishing is how much information is crammed into those fleeting seconds. From a signal lasting less than a heartbeat, scientists can extract the black hole's masses down to a fraction of a percent, their distances to within a few 100 million light-years, even the angle at which they're spinning relative to their orbit. It's like reconstructing the entire history of a car crash from the sound of the impact, and the chirps aren't all the same. Some rise slowly, like the drawn-out groan of a massive pair of black holes circling each other for eons. Others skyrocket in pitch almost instantly, the signature of lighter objects whipping around at dizzying speeds before merging. Each variation is a clue, helping astronomers piece together the demographics of black holes across the universe. Some chirps even echo with overtones, faint secondary frequencies that ring like harmonics on a guitar string, revealing the newly formed black hole's size and shape in the moments after collision. This is the power of gravitational wave astronomy, turning vibrations in spacetime into a detailed biography of the universe's most extreme events. Every chirp is a story, one written not in light or matter, but in the warping of space itself. And with every new detection, we're learning to read those stories more clearly, uncovering secrets hidden in the ripples of the cosmos. Einstein's theory of general relativity has survived every test thrown at it for over a century, but gravitational waves are putting it through trials unlike anything before. These ripples in spacetime aren't just cosmic messengers, they're precision instruments probing the fabric of reality under conditions so extreme they dwarf anything in our solar system. Every collision, every chirp carries subtle fingerprints that either confirm Einstein's vision or reveal where it might start to fray. Take the way gravitational waves propagate. According to relativity, these ripples should travel at the speed of light, unimpeded by anything in their path. When LIGO and Virgo detected the neutron star merger GW170817 in 2017, telescopes simultaneously caught the explosion's light. The gravitational waves arrived just 1.7 seconds before the gamma rays after journeying 130 million light-years. That near-perfect alignment confirmed Einstein's prediction with staggering precision. If gravity had even a tiny mass, as some modified theories suggest, the waves would have lagged behind. Instead, they raced across the cosmos neck and neck with light, a triumph for relativity. But the real stress test comes from the wave's shapes. As black holes spiral toward collision, their gravitational waves carry intricate harmonics, subtle overtones that should perfectly match relativity's equations. LIGO detectors have scrutinized these waveforms down to fractions of a percent, hunting for discrepancies. So far, Einstein's math holds, even in the violent chaos of a merger where spacetime warps beyond recognition. The signals align flawlessly with predictions. That's like dropping a grand piano from orbit and finding every note still perfectly in tune when it hits the ground. Yet the most brutal test lies in the aftermath of a collision. When two black holes merge, the new, distorted black hole rings down, vibrating like a struck bell. The tone and decay of this ringing encode the object's mass and spin, but also something deeper. According to relativity, only certain frequencies should exist, cleanly fading as the black hole settles into silence. Any extra tones or prolonged echoes could hint at exotic physics, perhaps extra dimensions or quantum foam frothing at spacetime's edges. Early analyzers show no such anomalies, but with more sensitive detectors, even fainter whispers might reveal cracks in Einstein's edifice. Then there's the puzzle of dispersion. In some alternative gravity theories, gravitational waves of different frequencies travel at slightly different speeds, like colors in a prism. LIGO observations rule this out too. High-frequency waves from a merger's final milliseconds arrive in lockstep with lower-frequency ones from earlier in the spiral, another win for relativity. What makes these tests so revolutionary is their sheer brutality. Earth-based experiments can't replicate the crushing gravity near black holes, where space-time curves so sharply it folds back on itself. But gravitational waves bring those extreme conditions to us, encoded in every ripple. Each detection is like receiving a cosmic telegram from a realm where physics operates at its limits, and so far, Einstein's rules still reign supreme. Yet the quest isn't just about confirmation. Somewhere in the faintest tremors of a distant collision, there might lurk a deviation too subtle to spot until now. Future detectors like the space-based LISA mission or next-generation ground observatories will push these tests further, hunting for relativity's breaking point. Because if Einstein's theory finally stumbles, the universe has a new story to tell. Black holes don't just collide, they pirouette, twisting space-time around them like cosmic tornadoes. And gravitational waves are the only way to catch them in the act. When LIGO detects a merger, it's not just measuring masses, it's deciphering spins, those elusive rotations that reveal how black holes lived before they died. Imagine trying to reconstruct a ballet from the vibrations left in a pond. That's the precision required to tease apart these spins, encoded in the subtle warping of each gravitational wave. The secret lies in the waveform's distortion. As two black holes spiral inward, their spins drag spacetime along with them, imprinting a distinctive fingerprint on the ripples. If both are spinning rapidly in the same direction as their orbit, the signal becomes louder and lasts longer. But if one spins backward like a rogue dancer out of sync, the waveform twists in unexpected ways. Scientists can even measure how tilted these spins are relative to the orbit, clues to whether the black holes grew steadily from a collapsing star or were flung together by chaotic cosmic encounters. Some findings defy expectations. Take GW 150914, the first detected merger. One black hole was spinning at least 20% as fast as Einstein's theory allows, a dizzying pace that suggests it grew by devouring matter or merging with others long before LIGO heard its final act. Others, like GW 190412, involved black holes with barely any spin at all, hinting at solitary lives where they formed from stars that collapsed without a twirl. Then there are the anomalies. GW 190521 featured a black hole spinning so fast it flirted with the theoretical maximum, a speed where spacetime itself struggles to keep up. Such extreme rotations challenge our models of how matter behaves under gravity's ultimate grip. Even stranger are misaligned systems, where black holes spin at odd angles to their orbit, suggesting violent origins in dense star clusters where gravitational encounters sent them tumbling into unlikely partnerships. These spins aren't just curiosities, they're cosmic history books. A rapidly spinning black hole might have grown by steadily slurping gas from a companion star, while a slow spinner could be the product of a messy, asymmetric collapse. Aligned spins often point to binary stars that lived and died together, while wild misalignments suggest black holes captured by chance, their spins frozen in time from separate births. With each new detection, patterns emerge. Binary black holes born together tend to have matched moderate spins. Those forged in stellar chaos, their spins are all over the map. And when mergers create new black holes, their spins become a blend of the parents, like mixing two whirlpools into one. This isn't just about cataloging rotations. Spin measurements test relativity's limits. Does spacetime really warp as predicted around these ultra-fast rotators? They also influence how black holes recoil after merging, sometimes kicking the newborn black hole across space at speeds over 3 million miles per hour. Every chirp carries a spin story. Some whisper of orderly stellar lives, others scream of violent cosmic bar fights. And as detectors grow more sensitive, we'll hear even fainter tales of ancient black holes spinning since the dawn of time, or ones so distorted they stretch the very definition of a black hole. The universe's darkest dancers are finally showing their moves, and gravitational waves are the spotlight. For decades, black holes came in two sizes, small and impossibly huge. On one end, stellar mass black holes weighing a few times the sun's mass, born from collapsing stars. On the other, supermassive giants lurking in galactic centers, millions or even billions of times heavier. But what about the middle? Where were the missing links? Black holes too large to form from a single star's death, yet too small to anchor a galaxy. Gravitational waves finally delivered the answer with GW190521, a detection that unveiled one of the universe's rarest beasts, an intermediate mass black hole. This cosmic Goldilocks, 142 times the mass of the Sun, wasn't just filling a gap in the catalog. Its existence rewrote the rules of black hole formation. Stellar collapse can't explain objects this hefty. Stars that massive typically blow themselves apart in supernova, leaving nothing behind. Instead, this black hole was likely born from a chain reaction, smaller black holes merging in dense stellar environments, growing over generations like a snowball rolling downhill. The signal told the story. The final merger involved a 66 solar mass black hole tangoing with an 85 solar mass partner, their collision echoing across the cosmos. What makes these middleweight black holes so elusive? They're orphans drifting far from the bright galactic centers where telescopes usually hunt. Without gravitational waves, we'd have almost no way to spot them. But LIGO detection proved they're out there, and more common than we thought. Follow-up studies suggest such mergers might happen thousands of times a year across the universe, hidden in the darkness between stars. The implications are staggering. Intermediate mass black holes could be the seeds of their supermassive cousins, growing by swallowing stars, gas, and other black holes over eons. Some might even power faint, wandering quasars, lonely beacons in the cosmic void. Others could solve the mystery of ultraluminous X-ray sources, bizarre objects that shine brighter than any known star system. But GW190521 raised new questions too. How did its two precursor black holes get so large? Were they themselves products of earlier mergers, a cosmic family tree of violence? And why does their collision match so perfectly with models when their size defies conventional formation? Every answer peels back another layer, revealing a universe far more dynamic and far more brutal than we ever imagined. With each new detection, the middle ground of black holes becomes less mysterious. Future observatories like the space-based LISA mission could catch these mergers earlier in their death spiral, tracing their origins back to star clusters or dwarf galaxies. Others might reveal even heavier intermediates, blurring the line between stellar and supermassive. One thing's certain, the cosmos doesn't do gaps. For every blank space in our maps, there's a hidden chapter waiting to be heard if we know how to listen. One of cosmology's greatest mysteries isn't hidden in the distant past, it's unfolding right now, in the way our universe stretches and grows. For years, scientists have wrestled with the Hubble constant, the number that describes how fast the cosmos is expanding. But there's a problem. Two leading measurement methods disagree, and the gap between them is widening. Enter gravitational waves, offering a third path to crack this puzzle, one that doesn't rely on light at all. When LIGO and Virgo detected the neutron star collision GW170817, they didn't just capture spacetime ripples, they pinpointed the event's distance with astonishing precision. How gravitational wave signals encode how much spacetime stretched during their journey, revealing exactly how far they've traveled. Meanwhile, telescopes identified the host galaxy, measuring how fast it's moving away from us due to cosmic expansion. Combining these gave a brand new Hubble constant measurement, 70 kilometers per second per megaparsec, with an uncertainty of just 10%. The brilliance. This method bypasses the cosmic distance ladder entirely, sidestepping the assumptions that fuel the ongoing debate. The tension is stark. Traditional methods using Cepheid variable stars and supernova peg the expansion rate around 73, while measurements of the cosmic microwave background suggest 67. Gravitational waves land right in the middle, close enough to tantalize, yet precise enough to deepen the mystery. If future detections refine this approach, they could reveal whether the discrepancy stems from measurement errors, unknown physics, or something far stranger, like dark energy evolving over time. What makes this revolutionary isn't just the number, it's the independence of the data. Previous methods relied on chains of assumptions. Cepheids require calibrating brightness with parallax. The cosmic microwave background hinges on our model of the early universe. But gravitational waves, they measure distance directly through spacetime distortion, no intermediate steps needed. It's like swapping a rickety rope bridge for a steel beam. Suddenly, the footing feels far more solid. The stakes couldn't be higher. If the tension persists, it might hint at exotic particles, extra dimensions, or flaws in our understanding of gravity. Some theories propose dark energy growing stronger. Others suggest the Hubble constant isn't constant at all. Gravitational waves offer a clean test, and with upgrades to LIGO and future detectors like the Einstein telescope, each new merger will sharpen the picture. This isn't just about solving a textbook disagreement. It's about rewriting the story of our universe's fate. Faster expansion could mean a lonelier future where galaxies vanish beyond an unreachable horizon. Slower expansion might signal a cosmos that eventually collapses. Gravitational waves, the silent messengers of spacetime itself, are now guiding us toward answers, one collision at a time. The universe loves to surprise us not just with what we can see, but with what might be hiding in the shadows. Among the most tantalizing mysteries are exotic compact objects, theoretical beasts that push the boundaries of known physics. These aren't your ordinary black holes or neutron stars. Imagine objects made of densely packed bosons, ghostly particles that could form vast, invisible stars or wormholes, cosmic shortcuts through spacetime itself. Gravitational waves are our best shot at uncovering these phantoms because, unlike light, they can't be hidden. Take boson stars, for example. If they exist, they'd be colossal structures built entirely from exotic particles like actions, hypothetical remnants of the early universe. Unlike black holes, they wouldn't have event horizons, no point of no return, but they'd still warp spacetime dramatically. When two boson stars collide, their gravitational wave signature would be subtly different from black hole mergers. Instead of the sharp chirp followed by silence, the waves might echo with faint aftertones, like a bell ringing in reverse as the stars pass through each other before merging. LIGO hasn't found one yet, but with upgrades, even these whispers could be snatched from the cosmic static. Then there's the holy grail, wormholes. Einstein's equations allow for these spacetime tunnels, but do they actually exist? If two wormholes connected distant parts of the universe were to vibrate, gravitational waves could carry their unique fingerprint. The signal might show bizarre distortions, sudden frequency jumps or echoes, as if the waves traveled through some unseen corridor. Some theories even suggest certain black hole mergers might actually be wormholes snapping shut, producing a telltale pop in the waveform that defies relativity's predictions. The hunt isn't just academic. Finding these objects would rewrite the rules of physics. Boson stars could solve the dark matter puzzle, their immense gravity sculpting galaxies without ever emitting light. Wormholes, if stable, would force us to confront whether interstellar travel or even time travel is fundamentally possible. And there are wilder ideas out there. Gravistars, hypothetical objects with cores of exotic vacuum energy, or fuzzballs, string theories alternative to black holes, where the event horizon is replaced by a tangled web of cosmic strings. Gravitational waves are the ultimate cosmic sieve, filtering out the impossible. Every merger LIGO detects either matches Einstein's predictions or doesn't. So far, black holes and neutron stars fit the mold. But as detectors grow more sensitive, the odds of catching something truly strange go up. It might start with a single anomaly, a waveform that wobbles where it should stay smooth, or a collision that leaves no remnant behind. One deviation and suddenly the universe gets a lot weirder. The stakes: imagine confirming that dark matter isn't just an invisible haze, it's gathered into massive, intangible structures orbiting galaxies. Or discovering that spacetime isn't just curved, it's punctured with tunnels. These aren't sci-fi fantasies, they're testable hypotheses, and gravitational wave astronomy is the key. Every new detection is a roll of the dice, and the universe has been playing this game far longer than we have. Somewhere in the static of the cosmos, beneath the crashes of black holes and neutron stars, there's a whisper, a murmur so faint it's drowned out by the universe's louder symphonies. But this isn't random noise. It's the stochastic gravitational wave background, the collective hum of every unresolved collision, every distant cosmic shudder too weak to pick out individually. Think of it like standing in a crowded stadium. You might hear the roar of the crowd, but only the closest shouts stand out. Gravitational waves work the same way. LIGO detected the shouts, the loud, nearby mergers, but the murmurs of millions of ancient black holes, neutron stars, and maybe even phenomena we haven't imagined. That's the background, and finding it would open a window into the universe's most crowded, violent eras. This hum isn't just white noise, it's a fossil record. Some of these waves could have been traveling for billions of years, carrying echoes from an epoch when galaxies were young and collisions happened far more often. Others might come from sources we've never seen. Primordial black holes forged in the Big Bang's chaos, cosmic strings vibrating from the universe's infancy, or even phase transitions in spacetime itself. The challenge: isolating this signal from the cacophony of detector noise, astrophysical interference, and the random jostling of atoms in LIGO mirrors. It's like trying to hear a single raindrop in a thunderstorm. That's where pulsar timing arrays come in. While LIGO hunts high-frequency waves from individual mergers, networks of millisecond pulsars, ultra-precise cosmic clocks scattered across the galaxy, act as a galaxy-sized gravitational wave detector. As these waves pass through Earth, they minutely alter the pulsar's ticks, creating a pattern that, over years of observation, reveals the background's low-frequency rumble. Early data hints at a possible signal, though confirmation is still pending. If real, it could be the first murmur of supermassive black hole binaries, pairs weighing billions of solar masses, slowly spiraling toward collisions that will shake the universe. The implications are staggering. A loud background might mean the early universe was a demolition derby of black holes, far more violent than models predict. A quieter one could hint at unknown physics smoothing spacetime's wrinkles. And if the signal wobbles in unexpected ways, that might point to exotic relics, leftover vibrations from cosmic inflation, or even defects in spacetime structure. This hunt isn't just about filling in a missing puzzle piece. It's about listening to the universe's baseline, the soundtrack of its history, written not in light but in the quiet tremors of spacetime itself. And with every year of data, the murmur grows clearer, bringing us closer to hearing the cosmos as it truly is, alive with invisible motion. Deep in the hearts of galaxies, where gravity rules supreme, two titans may be locked in an endless dance, supermassive black holes weighing millions or even billions of times more than our Sun, orbiting each other in slow, inevitable spirals. These aren't the fleeting mergers LIGO catches. They're relationships that play out over centuries, millennia, even epochs. And while their gravitational waves are too low-pitched for ground-based detectors to hear, a new era of space-based observatories is about to tune in. Imagine the Laser Interferometer Space Antenna, or LISA, a trio of spacecraft set to launch in the 2030s, flying in perfect formation 2.5 million kilometers apart. Unlike LIGO kilometer-scale arms, LISA vast triangle will catch waves with wavelengths so long they dwarf our entire planet. These are the ripples emitted by supermassive binaries, some so widely separated they take years to complete a single orbit. Their signals won't be chirps or crashes, but deep, resonant hums, a cosmic bassline threading through the universe. Why does this matter? Because supermassive black hole binaries are the ultimate architects of cosmic structure. When galaxies collide, as they often do, their central black holes eventually sink toward each other, trapped in a gravitational embrace. But here's the mystery. While simulations predict thousands of these pairs should exist, we've barely found any. Some stall just light years apart, their orbits refusing to shrink further, a cosmic standoff called the final parsec problem. Others might fling stars and gas away so violently they starve themselves of the very material needed to spiral closer. LISA will settle this debate by listening for their telltale hum. The waveforms will reveal everything: the black holes' masses, their spins, even the shape of their orbits. Some might trace graceful ellipses, relics of a galactic merger that threw them into perfect alignment. Others could be wildly eccentric, their paths scrambled by encounters with intruder black holes. And if we're lucky, LISA might catch a pair in the final years before collision, a crescendo that could teach us how galaxies like our own Milky Way and Andromeda will one day fuse into a single monstrous core. But the real prize lies beyond mere detection. Supermassive binaries are gravity's ultimate laboratories. Their slow, stately orbits probe general relativity over scales and time spans no experiment can replicate, searching for deviations that might hint at new physics. Some theories predict these waves should carry faint echoes of extra dimensions or quantum gravity effects, subtle distortions that only accumulate over years of observation. Others suggest the mergers might briefly warp spacetime so severely they create memory, a permanent deformation in the fabric of the universe. LISA won't just hear these giants. It'll trace their influence across cosmic history. By counting how many binaries exist at different stages, we'll learn how often galaxies merge and how black holes grow to such staggering sizes. Some signals might even come from the universe's first billion years, when the first supermassive black holes were born, seeding the structures we see today. This is gravitational wave astronomy's next frontier, not just listening for collisions, but tuning into the universe's deepest, most resonant frequencies, the slow, ancient songs of black holes that have danced together since before Earth formed. And when LISA finally opens its ears, the cosmos might just reveal its grandest symphony yet. Long before black holes danced or neutron stars collided, the universe itself was born in a fireball of unimaginable energy, and the echoes of that violent beginning might still ripple through spacetime today. These are primordial gravitational waves, the oldest vibrations in existence, generated in the first sliver of a second after the Big Bang, when the entire cosmos expanded faster than light itself. Unlike the waves we detect from black hole mergers, these wouldn't come from any celestial object. They'd be fossilized tremors from the birth of reality, carrying secrets about cosmic inflation, the mysterious process that blew up the universe from smaller than an atom to cosmic size in less than a blink. Detecting them would be like finding the universe's first breath. According to theory, inflation stretched quantum fluctuations in the infant cosmos into macroscopic ripples in spacetime. Some models predict these waves should still pervade the universe, albeit incredibly faint, a background hum with frequencies so low they'd make LIGO detections sound like shrieks. To catch them, we'd need a detector of staggering scale. Imagine a gravitational wave observatory in space, with arms millions of kilometers long, or one that uses not lasers but the precise timing of distant pulsars as its ruler. The prize, nothing less than a window into the Planck epoch, the era before time had meaning, when gravity and quantum forces were one. Primordial waves could reveal whether inflation really happened, and if so, what powered it. Was it an exotic energy field, as most theories suggest, or something stranger like a higher dimensional collision or a phase transition in the fabric of spacetime? Their polarization, the direction spacetime wobbles as the wave passes, might even hint at the quantum nature of gravity itself, bridging the last gap in modern physics. There's already been one tantalizing false alarm. In 2014, the BICEP 2 experiment claimed to spot primordial waves imprinted on the cosmic microwave background, only to later realize the signal was cosmic dust. But the hunt hasn't stopped. Upcoming missions like the European Space Agency's LIGO or NASA PICO aim to scour the microwave sky with far greater precision, while pulsar timing arrays keep listening for the low-frequency rumble of inflation's aftermath. If we ever detect these ancient ripples, they won't just tell us how the universe began. They'll reveal what came before, whether our cosmos is one of many in a vast multiverse, or if time itself has a shadowy origin story waiting to be heard. The universe's first whispers are still out there, trembling through the void, and we're just learning how to listen. If spacetime is a vast, invisible fabric, then gravity bends it like a lens, and gravitational waves are no exception. Just as light warps around massive objects, creating cosmic mirages called gravitational lenses, these ripples in spacetime can also be stretched, magnified, or even duplicated as they pass through dense regions of the universe. The result, a rare but powerful phenomenon, gravitationally lensed waves, where a single collision echoes across detectors multiple times, revealing secrets about everything from galaxy clusters to the nature of dark matter. Picture a black hole merger billions of light years away. As its gravitational waves travel toward us, they pass through a massive galaxy cluster, a gravitational buoy so dense it curves spacetime around it. The waves split, taking slightly different paths around the cluster's gravity well. One might arrive days, weeks, or even years before the other, like twin messengers from the same event. When LIGO catches these delayed signals, they're near-perfect copies, their waveforms almost identical but their volumes altered by the lens's distortion. It's cosmic karaoke, the same song sung twice at different volumes. This isn't just a curiosity, it's a precision tool. By comparing the lensed signals, scientists can map the invisible mass warping them. The time delay between echoes reveals the lens's distance and structure, while the amplitude changes expose how spacetime is stretched around it. And because gravitational waves pass through matter unimpeded, they probe regions opaque to light, like the hearts of galaxy clusters where dark matter lurks. A single lensed merger could weigh a cluster more accurately than any telescope, pinning down the distribution of both visible and invisible mass. The first candidate emerged in 2020 when LIGO detected a black hole collision with an oddly familiar waveform, almost a duplicate of an event months earlier. While not yet confirmed, such repetitions could become common as detectors grow more sensitive. Future observatories might catch waves lensed by supermassive black holes or even cosmic strings, hypothetical defects in spacetime from the universe's infancy. But the real magic lies in extreme lenses. Some galaxy clusters act like natural telescopes, magnifying distant objects behind them. If a gravitational wave passes through such a hotspot, it could be amplified enough to reveal mergers from the universe's first billion years, collisions now too faint to hear unaided. These primordial waves would carry whispers from the era when the first black holes formed, seeding the giants we see today. Lensed waves also offer a cruel twist. They can fool us. A magnified signal might masquerade as a nearby event, only for follow-up observations to reveal its true, ancient origins. Others could appear to violate relativity's speed limit, their delayed copies mimicking faster than light travel. Untangling these illusions requires patience and a new breed of algorithms designed to spot spacetime's hall of mirrors, yet the payoff is worth the puzzle. Every lensed wave is a free cosmic upgrade, turning random patches of the universe into gravitational telescopes. They'll map dark matter's clumps, test relativity over galactic scales, and maybe even catch echoes of collisions from universes beyond our own. The universe isn't just sending us messages, it's bending them into revelations. Dark matter remains one of the universe's greatest enigmas, invisible, untouchable, yet outweighing all visible matter 5-1. We know it's there because of its gravitational grip on galaxies, but its true nature has eluded every telescope and particle detector. Now, gravitational waves might offer a backdoor to this cosmic mystery, not by detecting dark matter directly, but by exposing its ghostly fingerprints on the collisions of black holes. Take a pair of black holes spiraling toward merger. According to conventional models, their orbits decay at predictable rates as they lose energy to gravitational waves. But what if dark matter is lurking nearby? If these black holes are embedded in a dense cloud of invisible particles, think of it as a cosmic fog. Their motion could subtly change. The dark matter's gravity would act like a drag, slowing their inspiral just enough to distort the gravitational wave signal. It's like trying to wade through a pool of molasses. The waves carry traces of that extra resistance, a telltale sign something unseen is at play. Some theories propose even wilder possibilities. Certain dark matter candidates, like ultralight bosons, could form vast, diffuse halos around black holes. As these black holes orbit, they'd interact with their own dark matter clouds, generating faint gravitational waves at distinct frequencies long before merger. LIGO hasn't spotted this yet, but future detectors might catch these whispers, a dark matter echo preceding the main event. Then there's the puzzle of black hole masses. Many mergers detected so far involve black holes in the so-called mass gap, heavier than typical stellar remnants but lighter than supermassive giants. Dark matter could explain this. If black holes grow by gobbling up invisible particles, they'd bulk up over time, landing in that elusive middle range. The distribution of masses we're seeing might literally map the hidden structure of dark matter halos. The clues don't stop there. Some models suggest dark matter could even catalyze black hole formation in the early universe, seeding the cosmos with primordial black holes that later merge. Others propose that certain dark matter particles, when annihilating near black holes, could produce energy that alters the merger's dynamics. If gravitational waves from a collision don't match predictions, dark matter might be the unseen hand tweaking the outcome. Of course, the hunt is filled with caveats. Detecting dark matter's subtle tweaks requires exquisite precision, the kind next-generation observatories like the Einstein telescope or Cosmic Explorer aim to achieve. False alarms lurk everywhere, from instrument noise to overlooked astrophysical effects. But the potential payoff, a new way to map the universe's invisible scaffolding, not by the light it blocks, but by the ripples it leaves in spacetime itself. Every black hole crash could be more than a spectacle of gravity. It might be a message in a bottle, carrying hints about the 85% of matter we've never seen. And as detectors grow sharper, even the faintest whispers of dark matter's presence could finally break its silence. Einstein's theory of general relativity has ruled our understanding of gravity for over a century, but somewhere in the subatomic chaos of quantum mechanics, it must break down. The problem, gravity's grip is so weak on tiny scales that no experiment has ever caught it misbehaving. That's where gravitational waves come in. These ripples carry more than just the fingerprints of black holes. They might encode the first whispers of quantum gravity, the elusive theory that could unite relativity with the quantum world. And the clues, they're hiding in deviations so small they'd make a proton look enormous. Take the aftermath of a black hole merger. As the newborn black hole settles into silence, it rings down, vibrating at specific frequencies predicted by relativity. But if spacetime has a quantum structure, a frothy, grainy texture at the tiniest scales, those vibrations could flicker in subtle, unexpected ways. Imagine dropping a pebble into a pond. On the surface, the ripples spread smoothly, but zoom in close enough and you'd see the water's molecular structure distorting the waves. Gravitational waves could reveal similar distortions in spacetime itself, if only we can measure finely enough. Some theories predict specific anomalies. Loop quantum gravity, for instance, suggests spacetime is woven from minuscule, indivisible loops. These could imprint jagged steps on gravitational wave signals, especially in the high-frequency chaos of a merger's final milliseconds. Other models, like string theory, propose extra dimensions curled into invisibly small shapes. If gravitational waves leak into those dimensions, their energy might dip at certain frequencies, like a song missing notes. Even tiny violations of relativity's speed limit, where high-frequency waves arrive nanoseconds earlier than lower ones, could hint at spacetime's quantum underpinnings. So far, LIGO data aligns perfectly with Einstein's predictions. But that doesn't mean quantum gravity isn't there. It might just be quieter than current detectors can hear. Future observatories like the Einstein telescope with its tenfold sensitivity boost could catch these whispers. They'll scrutinize the ring-down phase for faint overtones that shouldn't exist, or hunt for echoes, repeated bursts that might suggest gravitational waves are bouncing off microscopic spacetime structures. The stakes, beyond confirming quantum gravity, these deviations could reveal whether spacetime is fundamentally smooth or pixelated, whether extra dimensions exist, or even how the universe emerged from nothingness. Every black hole collision is a high-energy experiment we couldn't possibly recreate on Earth, a fleeting glimpse into the realm where gravity and quantum mechanics collide. And with each new detector upgrade, we edge closer to hearing the universe's smallest secrets. Beyond the familiar chirps and rumbles of black hole mergers lies an entirely unexplored frontier: gravitational waves vibrating at frequencies so high they dwarf anything LIGO can detect. These aren't the deep, slow waves from colliding black holes. Imagine instead a cosmic violin string plucked at frequencies 1,000,000 billion times higher, oscillations so rapid they'd make a neutron star's spin seem glacial. While current observatories are deaf to these whispers, their potential sources rewrite our understanding of reality itself. At the top of the speculative list, cosmic strings. Not the tangled yarn of childhood nightmares, but hypothetical defects in spacetime itself, infinitely thin, unimaginably dense filaments left over from the universe's birth. Picture the cracks formed when water freezes into ice, but etched into the fabric of reality. If these strings exist, they might occasionally snap or form loops that collapse violently, sending out bursts of high-frequency gravitational waves. Unlike black hole mergers, these wouldn't be one-off events but a constant cosmic crackle, a background hiss of snapping spacetime threads. The waves they'd produce could carry fingerprints of the universe's first trillionth of a second, clues about symmetry, breaking phase transitions when fundamental forces split apart forever. Then there's the inflationary epoch's wilder cousin, preheating. After cosmic inflation stretched the universe to macroscopic size, theorists believe it went through a turbulent, reheating phase where energy dumped into newly created particles. This chaos might have generated high-frequency gravitational waves with a distinctive statistical signature, like static from a detuned radio. If detected, they could reveal details about the inflation field's potential energy, the very mechanism that birthed the cosmos. Quantum gravity enthusiasts propose even stranger possibilities. If spacetime has a foamy texture at the tiniest scales, a seething mass of virtual black holes and wormholes flickering in and out of existence, particles moving through this quantum foam might emit high-frequency ripples. These wouldn't be the clean sine waves of classical physics, but jagged, stochastic bursts, like listening to spacetime's quantum static. Some models suggest these waves could be so energetic they briefly warp the speed of light itself, leaving telltale spikes in detectors sensitive enough to catch them. The technical challenges are staggering. To detect waves oscillating at terahertz frequencies or higher, we'd need instruments thousands of times more precise than LIGO. One proposal involves using crystals whose atomic lattices vibrate in sync with passing waves, converting spacetime ripples into measurable electric signals. Others envision networks of levitated nanoparticles, their quantum states perturbed by high-frequency spacetime vibrations. The payoff: a window into energy scales approaching the Planck length, where quantum mechanics and gravity finally shake hands. What makes this search revolutionary isn't just the exotic physics, it's the sheer audacity of probing eras before time had meaning. These waves might carry imprints from before the Big Bang, relics of a bouncing universe or colliding brains in higher dimensional space. Others could reveal dark matter particles annihilating in dense clusters, or even the formation of microscopic black holes in particle accelerators. Every unobserved frequency band is a locked door, and behind each could lie answers to questions we haven't yet learned to ask. The universe's soundtrack isn't just deep bass notes, it's a symphony spanning octaves we're only beginning to imagine. Black holes are cosmic minimalists, at least according to the no-hair theorem. This idea, rooted in Einstein's equations, suggests that black holes are the simplest objects in the universe, defined by just three features: mass, spin, and electric charge. No bumps, no scars, no memories of how they formed, just smooth, featureless event horizons. The name comes from a playful quip by physicist John Wheeler: black holes have no hair, meaning no extra details to fuss over. But what if they do? Gravitational waves are now probing this fundamental assumption, hunting for hidden complexity in the universe's darkest objects. Every time LIGO detects a black hole collision, it's essentially weighing and measuring the remnants, checking for deviations from the no-hair theorem's predictions. The math is exquisite. A newborn black hole's ring down, the final vibrations as it settles into equilibrium, should produce gravitational waves with specific frequencies and decay rates. If the object truly has no hair, those tones will be pure, like a perfectly tuned bell. But if there's hidden structure, perhaps quantum knots in spacetime, leftover imprints from the progenitor stars, or even remnants of exotic physics, the ring down might carry faint echoes or distorted harmonics, like a bell with cracks. Some theorists propose that black holes could grow quantum hair, subtle features tied to particles trapped just outside the event horizon. Others suggest that singularities, the infinitely dense cores of black holes, might not be points but fuzzy, extended structures that imprint on gravitational waves. Even tiny violations of the no-hair theorem could upend our understanding of how information escapes black holes, a puzzle at the heart of the infamous black hole information paradox. So far, LIGO observations align with the no-hair theorem's predictions, but the hunt is just beginning. Future detectors like the Einstein telescope or space-based LISA will catch ring-downs with unprecedented precision, listening for whispers of hidden structure. The stakes: if black holes turn out to have even the faintest hair, it would mean these cosmic vacuums aren't so simple after all, and that spacetime might hold secrets far stranger than relativity alone can explain. This isn't just about testing a quirky theorem. It's about asking whether black holes truly erase the past, or if the universe keeps subtle records in ways we're only beginning to decode. Every merger is a chance to scan the cosmic barber's chair, and gravitational waves are the finest comb we've ever had. Some signals from the cosmos refuse to play by the rules, like the whispers that might be echoing from black holes' very edges. These aren't the clean, predictable chirps LIGO was designed to catch. Instead, they're faint, repeating ripples that some researchers believe could betray the presence of structures just beyond the event horizon, structures that shouldn't exist if Einstein's theory holds perfectly. Dubbed gravitational wave echoes, these anomalies could hint at physics wilder than anything in our textbooks, from quantum fuzzballs to hidden dimensions. The controversy began with a subtle pattern buried in the data. After the explosive ringdown of certain black hole mergers, a handful of scientists claimed to detect faint, delayed repetitions like a shout bouncing off a distant canyon wall. If real, these echoes might suggest that black holes aren't the perfect, featureless voids predicted by general relativity. Instead, their event horizons might harbor exotic structures, perhaps quantum firewalls, microscopic Planck-scale bumps, or even remnants of the star that collapsed to form them. The implications would be staggering. Traditional black holes erase everything that crosses their threshold. But echoes, they'd imply something survives, even if just as a scrambled gravitational imprint. Skeptics argue these signals are noise artifacts of LIGO, immense sensitivity to random vibrations. After all, teasing echoes from the data requires statistical gymnastics, hunting for patterns so faint they blur into the background. Yet proponents counter with tantalizing correlations. In 2016, a team analyzing the first LIGO detections reported echoes cropping up milliseconds after the main signal, with a timing that matched predictions from certain quantum gravity models. Other studies found similar hints in later mergers, though always at the edge of detectability. The debate hinges on a critical question: are we seeing the first cracks in relativity, or just the limits of our instruments? What makes these echoes so revolutionary isn't just their existence, it's what they'd reveal about spacetime's fabric. Some theories suggest the echoes arise from a quantum mirror, just outside the event horizon, a boundary wherein falling matter gets trapped in a last-ditch quantum dance before vanishing. Others propose that black holes are actually fuzzballs, tangled knots of string theory filaments whose surfaces could reflect gravitational waves like a cosmic drumhead. Even wilder ideas involve spacetime fracturing into a fractal-like structure near the singularity, creating layered echoes that encode information about the black hole's hidden interior. The hunt is far from settled. New algorithms are sifting through LIGO data with sharper tools, while next-generation detectors like the Einstein telescope will boost sensitivity 100-fold. If echoes are real, they'd rewrite our understanding of black holes as cosmic vaults, not just swallowing information, but subtly leaking it back into the universe. Every merger becomes a potential Rosetta Stone, its reverberations carrying clues about the quantum underworld lurking beyond the point of no return. The echoes might be faint, but their message is deafening. The universe's darkest objects could be far stranger than we dreamed. Neutron stars are the universe's ultimate pressure cookers, cosmic remnants so dense that a single teaspoon of their material would weigh 1 billion tons on Earth. But these exotic objects aren't just silent orbs of compressed matter. Their surfaces might be constantly trembling with violent starquakes, massive fractures in their ultra-rigid crusts, and gravitational waves could be our key to listening in. Every time one of these quakes shakes a neutron star, it sends ripples through spacetime itself, carrying encoded details about what lies beneath the surface. Imagine a neutron star's crust as a crystalline shell 1 kilometer thick, harder than any material known to science, floating atop an ocean of neutron-rich superfluid. When stress builds from magnetic field shifts, sudden spin changes, or even asteroid impacts, this crust can crack catastrophically, releasing energy equivalent to hundreds of nuclear bombs. These quakes aren't just surface-level events. the vibrations penetrate deep into the star, bouncing between the crust and core like sonar pulses in a submarine. If the star's interior is layered with exotic states of matter, perhaps quarks freed from their atomic prisons or hyperons existing only under extreme pressures, the quake's gravitational wave signature would reflect that internal architecture. Detecting these tremors requires next-level sensitivity. Unlike the sharp chirps of black hole mergers, neutron star quakes would produce a hum of continuous gravitational waves, oscillating at frequencies between a few hundred and a few thousand hertz, the cosmic equivalent of a sustained violin note. Current detectors like LIGO aren't optimized for these tones, but upcoming upgrades and specialized observatories could change that. The trick is teasing out these faint signals from the cacophony of detector noise, a challenge akin to hearing a whisper in a hurricane. Why does this matter? Because neutron stars are nature's most extreme physics labs. Their interiors reach densities unreachable in any Earth-based experiment, where matter gets squeezed into forms we've only theorized. A quake's gravitational waves could settle debates about whether neutron star cores contain free quarks, hyperon soups, or even stranger phases like color superconductors. The vibrations might also reveal the star's exact size, a critical clue for understanding the equation of state of ultradense matter, which dictates how compressible neutron star material really is. Some models predict even wilder possibilities. If certain vibrations resonate at specific frequencies, they could amplify gravitational waves dramatically, a phenomenon called mode trapping, where the star acts like a cosmic tuning fork. Others suggest that starquakes might trigger magnetic reconfigurations so violent they briefly illuminate the star in X-rays, giving astronomers a rare chance to correlate gravitational wave data with electromagnetic signals. Already, there are tantalizing hints. In 2020, a gamma ray burst from a neutron star 25,000 light-years away coincided with a subtle disturbance in LIGO data, too faint to confirm but intriguing enough to spark new searches. Future missions like the Einstein telescope, with its planned tenfold sensitivity boost, could turn these whispers into headlines, mapping neutron star interiors with gravitational wave seismology. Each quake is a message in a cosmic bottle, carrying news from a realm where matter stops behaving normally and starts obeying rules we're only beginning to guess. And when we finally decode those vibrations, we won't just be studying stars, we'll be reading the recipe for matter itself, written in the shudders of spacetime. In the darkest corners of the universe, behind the impenetrable curtains of black hole event horizons, lurk the most forbidden objects in physics, naked singularities. These are the cosmic rule breakers, points of infinite density so extreme they defy Einstein's equations, yet unlike their well-behaved cousins hidden inside black holes, they have no event horizon to shield the universe from their chaos. According to Roger Penrose's cosmic censorship hypothesis, nature abhors such monstrosities, always cloaking them behind horizons to preserve causality. But gravitational waves might be about to expose them. Imagine two black holes spiraling toward collision, except one isn't a black hole at all, but a naked singularity. Unlike the orderly chirp of a standard merger, this event would send spacetime into a frenzy. Without an event horizon to smooth the transition, the singularity's infinite curvature could imprint wild, unpredictable oscillations on the gravitational wave signal, like a seismograph during an earthquake, but with spikes so violent they'd make LIGO algorithms scream in protest. Some models suggest these waveforms might even carry fractal-like patterns, repeating at finer and finer scales as the singularity's infinite density twists spacetime into knots. The hunt for these cosmic outlaws isn't just theoretical. Certain exotic objects like super-spinning neutron stars or collapsing dark matter cores could skirt the edge of cosmic censorship, forming naked regions just before full collapse. Others speculate that high-energy particle collisions might momentarily birth microscopic naked singularities, vanishing too quickly to destabilize reality, but leaving gravitational wave fingerprints in their wake. Even black hole mergers themselves could, under extreme conditions, momentarily expose their singularities during collision, an infinitesimal flash of cosmic indecency before the new horizon forms. If gravitational waves ever catch such an event, the implications would shake physics to its core. Naked singularities aren't just mathematical oddities, they're portals to realms where gravity and quantum mechanics merge, where time loops back on itself, and where predictability itself breaks down. Detecting one could force a rewrite of general relativity or reveal entirely new physics governing spacetime's extremes. So far, LIGO catalog shows no confirmed violations of cosmic censorship. But with every upgrade to detector sensitivity, the odds improve. Future observatories might catch singularities in the act, flashing their infinite density to the universe, if only for a fleeting moment. And if they do, the message will be clear: nature's most sacred rule has an exception, and the universe is far stranger than we dared to dream. Gravitational waves don't just ripple outward in random patterns, they carry a hidden signature in the way they stretch and squeeze spacetime, a fingerprint called polarization. Just as light waves can be polarized, vibrating in specific directions, gravitational waves exhibit their own distinct patterns of distortion, and those patterns could be the key to unlocking gravity's deepest secrets. Depending on which theory of gravity you subscribe to, Einstein's general relativity or one of its many challengers, these waves should twist spacetime in subtly different ways, leaving behind traces that future detectors might finally catch. General relativity predicts a straightforward polarization, two fundamental modes whimsically named plus and cross for how they deform a ring of test particles. Picture a circle of marbles floating in space. A plus wave would squash it vertically while stretching it horizontally, then reverse the motion like an accordion breathing in and out. The cross wave does the same but rotated by 45 degrees, creating an X-shaped wobble. These two modes are all relativity needs to describe gravity's ripples. But alternative theories, they're far more extravagant. Some modified gravity models, like scalar tensor theories, introduce an extra polarization mode, a breathing motion where the ring of marbles expands and contracts uniformly, as if spacetime itself were pulsing like a heartbeat. Others, such as massive gravity theories, predict longitudinal waves where particles get shoved forward and backward along the wave's path, like commuters in a subway car during rush hour. These exotic polarizations arise because alternative theories often propose new particles or fields that mediate gravity differently, adding wrinkles to spacetime's fabric that Einstein never anticipated. The challenge lies in detection. Current observatories like LIGO are primarily sensitive to the plus and cross modes, their L-shaped arms optimized for the stretches and squeezes relativity predicts. But next-generation detectors like the triangular LISA mission in space or the underground Einstein telescope will act as gravitational wave polygraphs, scrutinizing signals for hints of forbidden polarizations. By comparing how a wave distorts multiple detectors arranged in different orientations, scientists could spot anomalies betraying new physics. A single detection of a breathing or longitudinal mode would upend Einstein's legacy overnight. The stakes are cosmic. Polarization isn't just about how waves wiggle, it's a direct probe of spacetime's underlying structure. General relativity assumes spacetime is smooth and four-dimensional, but theories with extra dimensions or quantum granularity could imprint odd polarizations. Even dark energy might leave traces, subtly altering wave patterns over vast distances. Every gravitational wave is a message written in spacetime's alphabet. We've only just learned to read a few letters. The rest could spell out an entirely new theory of the universe. We've heard black holes collide, but what about the moment they're born? Gravitational waves might soon give us a front-row seat to one of the universe's most violent deliveries, the creation of a black hole itself. Picture a massive star, its fuel exhausted after millions of years of fusion. In its final seconds, the core collapses under its own weight, triggering a supernova explosion so powerful it outshines entire galaxies. Most of the star blasts into space, but the core keeps falling inward, shrinking until not even light can escape. That's the textbook version, but hidden in the chaos could be a gravitational wave signal, a momentary scream from spacetime as the black hole snaps into existence. These birth cries wouldn't sound like the chirps of merging black holes. Instead, they'd be short, sharp bursts less than a second long, carrying the fingerprint of the collapsing star's asymmetries. If the implosion isn't perfectly spherical, which it almost never is, the violent jostling of matter would send ripples through spacetime. The signal might start with low-frequency rumbles as the outer layers collapse, then spike into higher frequencies as the core reaches near infinite density. Some models even suggest a final pop as the event horizon forms, a spacetime shudder marking the point of no return. But stellar collapse isn't the only pathway to a black hole's birth. Exotic alternatives could leave even stranger gravitational wave signatures. Take the hypothetical collapse of a dark matter clump, an invisible, dense nugget of the universe's most mysterious substance. If these clumps exist and can collapse directly into black holes, they'd skip the light show entirely, leaving only a gravitational wave whisper as their birth announcement. Or consider the cosmic fireworks of a failed supernova, where a massive star implodes without the usual explosion. These unnovae could form black holes almost silently in optical telescopes but shout their arrival in gravitational waves. The challenge: these signals are fiendishly hard to catch. A collapsing star in our galactic neighborhood might only produce a wave strong enough to ripple LIGO detectors once every few decades. But next-generation observatories, like the Einstein telescope with its subterranean sensitivity, could hear these events across much of the visible universe. And if we get lucky, a nearby collapse, say, in the Large Magellanic Cloud, might deliver a signal so crisp it reveals not just the black hole's formation, but the star's rotation, the shape of its core, even the turbulence of its dying moments. The payoff goes beyond cosmic voyeurism. Catching a black hole's birth would solve long-standing mysteries, like whether supernova always accompany black holes or if some slip quietly into the dark. It could also reveal the mass gap, the puzzling absence of black holes between about 50 and 100 solar masses, a range too heavy for stellar collapse but too light for mergers. If we detect waves from this forbidden zone, it might mean black holes can grow through exotic means, like swallowing dark matter or merging in dense stellar nurseries. Most tantalizing is the chance to witness something truly unprecedented, a black hole forming through unknown physics. Quantum gravity theories suggest that at the final moment of collapse, spacetime might rebel against infinite density, producing a bounce or a burst of high-frequency waves. Others propose that primordial black holes forged in the Big Bang's fury could be collapsing today, their ancient deaths echoing across cosmic time. Every black hole we've detected so far is middle-aged, its origins a mystery, but gravitational waves could change that, letting us eavesdrop on their first breaths. And when we do, we won't just be watching a star die, we'll be seeing a black hole take its place in the cosmic dark. Wormholes, those hypothetical tunnels through space-time, aren't just the stuff of science fiction. If they exist, they might leave behind gravitational wave signatures so bizarre they'd make black hole mergers seem mundane. Picture a wormhole as a cosmic shortcut, a bridge connecting two distant points in space. But unlike black holes, which trap everything inside them, a traversable wormhole would theoretically allow matter, and even gravitational waves, to pass through. And that transit could create ripples in spacetime with features no natural collision could replicate. Imagine two black holes orbiting each other, except they're not black holes at all, but the mouths of a wormhole. As they spiral inward, their gravitational waves would follow the usual pattern at first, rising in pitch like a standard chirp. But the moment the mouths connect, the signal would twist into something unrecognizable. Waves passing through the wormhole's throat might emerge milliseconds later, creating eerie echoes in the data, like hearing the same note played twice, slightly out of sync. Some models even suggest resonant frequencies, where the wormhole acts like a spacetime flute, amplifying certain tones as waves bounce between its ends. Then there's the strangest possibility of all, a wormhole snapping shut. If the tunnel becomes unstable, its collapse could release a gravitational pop, a sudden, high-frequency burst unlike anything seen in black hole mergers. This wouldn't be the slow fade of a ring down, but a sharp cutoff, as if spacetime itself hiccuped. Certain theories even predict a signature anti-chirp, where the frequency plummets instead of rising, a gravitational wave equivalent of a record playing backward. The real smoking gun, though, might come from distortion. As gravitational waves traverse a wormhole, the extreme curvature of its throat could warp their polarization, twisting the plus and cross modes into something unrecognizable. Alternative theories of gravity, like those with extra dimensions, might imprint even wilder patterns, perhaps a mix of breathing and longitudinal modes that violate Einstein's predictions outright. Of course, no confirmed wormhole signal exists yet, but as detectors grow more sensitive, the odds improve. Future observatories like LISA or the Einstein telescope could spot these anomalies buried in the cosmic static. Every unexplained echo, every anti-chirp or polarization oddity raises the tantalizing question: are we hearing the universe's plumbing, the hidden tunnels stitching spacetime together? Finding one wouldn't just revolutionize physics, it'd rewrite our map of reality itself. Dark energy is the universe's greatest unsolved riddle, an invisible force stretching spacetime apart faster and faster, defying gravity's pull. For decades, we've studied its effects through distant supernova or the cosmic microwave background. But now, gravitational waves offer a radical new tool, a way to map dark energy's influence not by the light it dims, but by the ripples it distorts. Every black hole or neutron star merger detected carries a hidden clue: its distance. Gravitational waves encode how much the universe has expanded during their journey, revealing how far they've traveled. But here's the twist: if dark energy's strength has changed over cosmic history, mergers from different eras would show anomalies in their distribution. Imagine the universe as an inflating balloon. If dark energy suddenly grew stronger, mergers from that epoch would appear oddly spaced, like dots on the balloon's surface, suddenly spreading apart faster than expected. Current catalogs already hint at possibilities. Mergers detected from around 7 billion years ago, when dark energy supposedly became dominant, could carry subtle imprints off this transition. Future observatories like the Einstein telescope will scan even deeper, catching collisions from the universe's adolescence. If the merger rate spikes or dips at specific distances, it might reveal dark energy's evolving nature, perhaps weakening in the past or clustering irregularly across space. The real power comes from combining gravitational waves with traditional probes. When LIGO detects a merger, telescopes can pinpoint its host galaxy, measuring how fast it's receding due to expansion. By cross-referencing these distances with the wave's own cosmic yardsticks, scientists can test if dark energy's push varies across spacetime. A discrepancy here could upend our simplest models, suggesting dark energy isn't a constant force but a dynamic field, decaying or interacting with matter in ways we've never seen. Some theories go further. If dark energy stems from vacuum fluctuations in spacetime, its density might fluctuate on colossal scales. Gravitational waves traversing these regions could stretch or compress slightly, their waveforms bearing faint scars of the journey. Others propose that dark energy's influence could warp the very propagation of gravitational waves, subtly altering their speed over billions of light years, a deviation so tiny only future space-based detectors like LISA could catch it. This isn't just about refining a number, it's about uncovering whether dark energy is a cosmological constant, a new fundamental force, or something far stranger. Every merger is a timestamp, a marker in spacetime's expansion. And as the catalog grows, we're not just listening to the universe's explosions, we're decoding the hidden architecture of its acceleration. Einstein's smooth spacetime might be an illusion, a cosmic mirage hiding a turbulent quantum reality beneath. At scales 1 trillion times smaller than an atom, spacetime could be a seething froth of virtual black holes and wormholes blinking in and out of existence, a turbulent realm physicists call quantum foam. For decades, this idea lived purely in theory, impossible to test directly. But now, gravitational waves might offer our first glimpse into this subatomic chaos, if only we can decode the subtle distortions they pick up while traversing the universe. The logic is simple: gravitational waves stretch and squeeze spacetime as they travel. If that spacetime has a foamy texture at microscopic scales, the waves wouldn't glide through unimpeded, they'd scatter like light passing through frosted glass. Over billions of light years, these tiny deflections could accumulate, warping the wave's shape just enough to leave faint fingerprints. Some models predict high-frequency jitters superimposed on the signal, a stochastic crackling from spacetime's underlying graininess. Others suggest the waves might slow down slightly at certain frequencies, as if fighting against the foam's resistance, the most tantalizing possibility. Gravitational wave echoes delayed repetitions of the main signal caused by waves taking slightly different paths through the quantum labyrinth. So far, LIGO detections align perfectly with pristine, smooth spacetime. But that doesn't mean quantum foam isn't there. It might just be too subtle for current detectors. Future observatories like the Einstein telescope, with its 100-fold sensitivity boost, could hunt for these anomalies in the most extreme environments. Black hole mergers are ideal test cases. Their highest frequency gravitational waves, produced in the collision's final milliseconds, interact more strongly with the foam's hypothetical microstructure. If those frequencies arrive slightly scrambled or dimmed compared to Einstein's predictions, it could hint at spacetime's hidden graininess. The implications stretch beyond mere curiosities. Quantum foam models vary wildly. Some predict foamy structures the size of the Planck length, a vanishingly small 10 to the minus 35 meters. Others suggest larger bubbles from extra dimensions or string theory. Gravitational waves could distinguish between these ideas based on how they distort. For instance, certain string theory variants predict foamy spacetime would act like a dispersive medium, bending high-frequency waves more than low ones, an effect that would manifest as a smear in the signal's timing. Loop quantum gravity, meanwhile, might imprint a distinctive statistical noise pattern on the waveforms, like static from a detuned radio. Of course, alternative explanations lurk everywhere. Interstellar gas, cosmic strings, or even instrumental noise could mimic some foam-like effects. That's why researchers are developing sophisticated filtering techniques, isolating quantum signatures from mundane astrophysical interference. The key is to find correlations. If multiple mergers from different distances all show the same distortion patterns, it becomes harder to blame local phenomena. This isn't just about validating abstract math. If spacetime foam exists, it would mean reality isn't fundamentally continuous but pixelated, like a cosmic digital screen. Such a discovery would bridge the last gap between quantum mechanics and gravity, revealing how spacetime itself emerges from something deeper. It might even answer whether our universe is a hologram, a lower-dimensional projection encoded on distant boundaries. Every black hole collision sends waves through billions of years of spacetime's history. Hidden in their faintest trembles could be echoes from the moment physics was born, a whisper that reality, at its core, is far wilder than it appears. What if the universe has more dimensions than we can see, hidden layers of reality curled up so tightly they evade our senses? String theory, one of the most ambitious frameworks in physics, suggests exactly that: extra dimensions beyond the familiar four, vibrating at scales a billion times smaller than an atom. While these dimensions remain speculative, gravitational waves could be the key to uncovering them, not by direct observation, but by catching the faint distortions they imprint on spacetime's ripples. Imagine a gravitational wave traveling across the cosmos. According to general relativity, it should stretch and squeeze spacetime in predictable ways. But if extra dimensions exist, some of the wave's energy might leak into these hidden realms, subtly altering the signal by the time it reaches our detectors. The effect would be minuscule, perhaps a dip in the wave's amplitude or a slight shift in its frequency, but mathematically distinct from noise. Some models even predict resonant frequencies, where waves matching the curled-up dimension scale would disappear entirely, like sound waves canceling each other out. The most tantalizing possibility comes from string theory's brain-world scenarios. In these models, our observable universe is a three-dimensional brain floating in a higher dimensional bulk. Black hole collisions could momentarily create vibrations that propagate into the bulk, leaving behind echoes or waveform distortions that betray the extra dimension's presence. Certain versions of this idea suggest that high-energy mergers might even produce microscopic black holes that evaporate instantly via higher dimensional effects, a process that could imprint a telltale burst of high-frequency gravitational waves. Current LIGO data shows no definitive signs of extra dimensions, but that doesn't mean they're not there. The energy scales required to excite these hidden layers might be beyond LIGO reach, accessible only to future detectors like the Einstein telescope or space-based observatories probing lower frequency waves. Alternatively, the dimensions could be so tightly curled that their effects emerge only in the quantum foam of spacetime itself, requiring radical advances in waveform analysis to spot. What makes this hunt revolutionary isn't just the potential discovery, it's the way gravitational waves bypass traditional limits. Particle colliders like the LHC hunt for extra dimensions by smashing protons together, hoping to glimpse debris ejected into higher realms. But gravitational waves don't need collisions. They carry the imprint of spacetime's full geometry, offering a cleaner, more direct test. A single anomalous waveform could reveal not just the existence of extra dimensions, but their size, shape, and even how they're folded into the fabric of reality. For now, the higher dimensions remain a beautiful hypothesis, but with every new gravitational wave detection, we're not just listening to black holes, we're tuning our instruments to the universe's hidden symphony, one where the notes might be vibrating in realms we've yet to imagine. Right now, the hunt for gravitational waves is just beginning, because the detectors we have today are like listening to the ocean with a seashell compared to what's coming next. The next generation of observatories, like the Einstein telescope and Cosmic Explorer, aren't just upgrades, they're quantum leaps into a new era of cosmic discovery. Imagine tuning a radio from static to crystal clear music. That's the kind of transformation these instruments promise, unlocking secrets about black holes, the Big Bang, and even the fabric of spacetime itself. The Einstein telescope, set to begin construction underground in Europe by the end of this decade, is a monster of sensitivity. Unlike LIGO L-shaped arms, it'll form a triangle with 10-kilometer-long tunnels shielded from surface noise a kilometer beneath the Earth. This design lets it catch waves 10 times fainter than current detectors, listening deeper into the universe's past. Its frequency range will stretch from just 1 Hz, low enough to hear supermassive black holes spiraling for years before collision, up to 10,000 Hz, where the quantum jitters of neutron star crusts might finally become audible. The goal, a cosmic census of black holes, mapping millions of mergers across cosmic time to trace how these dark giants evolved from the universe's infancy. Meanwhile, across the Atlantic, Cosmic Explorer aims to push ground-based detection to its absolute limit. With 40-kilometer arms, 4 times longer than LIGO, it'll spot collisions so distant their light hasn't even reached us yet. Picture catching gravitational waves from the cosmic dawn, when the first stars and black holes ignited. This machine could hear neutron star mergers from every corner of the observable universe, turning rare events into routine detections. But its real power lies in precision. By measuring waveforms with unprecedented clarity, it might spot deviations from Einstein's predictions, tiny cracks in relativity that hint at quantum gravity or extra dimensions. Then there's LISA, the Laser Interferometer Space Antenna, a trio of spacecraft set to launch in the 2030s. Floating 2.5 million kilometers apart, they'll catch low-frequency waves impossible to detect on Earth, like the million-year duets of supermassive black holes long before they merge. LISA data could reveal how galaxies grew by tracking these mergers across cosmic time, while also hunting for exotic ripples from cosmic strings or the Big Bang itself. But the future isn't just about bigger hardware, it's about smarter listening. Machine learning algorithms will soon sift through detector noise in real time, spotting signals too faint or too fleeting for human analysts. Some projects even propose using quantum entanglement to boost sensitivity, linking mirrors separated by kilometers as if they were a single quantum object. The result, detectors so precise they could measure a proton's width across interstellar distances. What will these instruments reveal? Possibly everything from the birth cries of the first black holes to the murmurs of dark matter particles colliding. They might catch neutron stars tearing apart in quark-nova explosions, or witness the death of a singularity as it tunnels into another universe. And if we're exceptionally lucky, they'll stumble upon something entirely unexpected, a signal so bizarre it rewrites the laws of physics. The golden age of gravitational wave astronomy isn't on the horizon. It's already here, and with each new detector, we're not just expanding our toolkit. We're rewiring our ears to hear the universe as it truly is, a symphony of space-time, playing in frequencies we've only just begun to imagine. Gravitational wave astronomy isn't just for professional researchers in lab coats. Some of the most exciting discoveries in this field are happening thanks to everyday people sitting at their kitchen tables. Projects like Gravity Spy have cracked open the door to citizen science, inviting amateur enthusiasts to help sift through the mountains of data generated by detectors like LIGO. This isn't busy work. Volunteers are playing a real, meaningful role in separating cosmic signals from the chaotic noise of the universe, and in the process, they're uncovering anomalies that even algorithms might miss. The challenge is immense. LIGO detectors are so sensitive they pick up everything from distant black hole mergers to the rumble of trucks passing miles away. Sorting through this data requires identifying and categorizing thousands of glitches, brief disturbances that can mimic gravitational waves. Machine learning helps, but it's not perfect. That's where human intuition comes in. Gravity Spy trains volunteers to recognize different types of noise, from scratchy blips to sinusoidal whistles, using an interface that feels almost like a cosmic puzzle game. The goal, to clean up the data so scientists can focus on the real events buried within. What makes this collaboration so powerful is the way it taps into pattern recognition, something human brains excel at. A volunteer might spot a recurring glitch that algorithms lumped into the wrong category, or even flag something entirely new. In one case, participants helped identify a mysterious kilonova echo pattern that turned out to be an artifact of the detector's mirrors, a subtle distortion that could have muddied observations of real neutron star collisions. Other projects like Zooniverse's Supernova Hunters have shown how crowdsourcing can lead to breakthroughs. It's not hard to imagine a similar eureka, a moment in gravitational wave science. But the impact goes beyond data processing. By involving the public, projects like Gravity Spy demystify cutting-edge research, turning abstract concepts into something tangible. Participants aren't just clicking buttons, they're learning how detectors work, why glitches happen, and what gravitational waves actually sound like. Some volunteers have even co-authored scientific papers, their contributions formally recognized alongside career astrophysicists. It's a reminder that science isn't an exclusive club, it's a collective effort fueled by curiosity at every level. The future of citizen science in this field is wide open. As detectors grow more sensitive, the data deluge will only intensify, and fresh eyes will be crucial for spotting the unexpected. Who knows, the next person to uncover a bizarre glitch or even a genuine gravitational wave signal might be a high school teacher, a retired engineer, or a student halfway across the world. In the hunt for spacetime's whispers, every perspective counts. For centuries, astronomy relied on a single language, light, to decode the universe's mysteries. But gravitational waves didn't replace that vocabulary. They expanded it, joining forces with other cosmic messengers to tell a richer, more nuanced story. Think of it like assembling a jigsaw puzzle where each piece comes from a different spectrum. Gamma rays blazing from collapsing stars, neutrinos slipping through matter like ghosts, and now spacetime ripples carrying whispers of invisible collisions. Together, they don't just fill gaps, they reveal a cosmos far more dynamic and interconnected than we ever imagined. Take neutron star mergers, for example. When LIGO and Virgo detected GW170817, the gravitational wave signal alone was groundbreaking. But the real revolution began when telescopes spotted the accompanying kilonova, a flare of gamma rays, X-rays, and optical light. That explosion didn't just confirm the wave's origin, it unveiled the cosmic forge where gold and platinum are born. Meanwhile, detectors like IceCube hunted for neutrinos from the event, particles that could reveal how matter behaves under conditions more extreme than any lab could replicate. Each messenger brought a unique perspective. Gravitational waves mapped the merger's dynamics, light revealed its chemical aftermath, and neutrinos probed the energy fluxes hidden deep within. This multi-messenger approach isn't just additive, it's transformative. Gamma-ray bursts, for instance, have long puzzled astronomers. Some last milliseconds, others linger for minutes. But when gravitational waves joined the conversation, they exposed a critical distinction. Short bursts often come from neutron star collisions, while longer ones might trace back to collapsing massive stars. Without spacetime ripples, we'd still be guessing. Similarly, neutrino observatories occasionally catch ultra-high-energy particles with no obvious source. Now, gravitational wave alerts give them a roadmap, narrowing the search to cataclysms like supernova or black hole births that might otherwise escape notice. The synergy goes deeper. Dark matter searchers traditionally rely on indirect clues, galaxy rotations, gravitational lensing. But if dark matter interacts with itself, as some theories suggest, its collisions in dense regions like galaxy cores could produce faint gravitational waves. Pair those with neutrino or gamma ray signatures from the same event, and suddenly you've triangulated the invisible. Even cosmic rays, high-energy particles from deep space, gain new context when cross-referenced with gravitational wave catalogs. A mysterious cosmic ray spike might align with a black hole merger's afterglow, hinting at particle acceleration mechanisms we've never seen. What makes this era so exhilarating is how these messengers compensate for each other's blind spots. Light gets absorbed or scattered. Neutrinos rarely interact. Gravitational waves pass through everything but reveal little about composition. Together, they're the ultimate cosmic detective team. When a supernova explodes, neutrinos arrive first, giving hours of warning before the light show begins. gravitational waves could one day provide similar alerts for black hole mergers, guiding telescopes to capture the moment a star vanishes into darkness. The future holds even wilder possibilities. Imagine catching a gamma-ray burst, gravitational waves, and a neutrino swarm all from the same event, a trifecta that could unravel the physics of quark stars or cosmic strings. Or consider fast radio bursts, those enigmatic deep space radio pulses. If gravitational waves ever trace one back to a magnetoquake or neutron star collision, it would solve a mystery that's baffled astronomers for decades. This isn't just about collecting data, it's about seeing the universe in layers, like peeling an onion where every skin reveals a new dimension of reality. Gravitational waves didn't replace light or neutrinos, they gave them new meaning, turning solitary notes into a symphony. And as detectors grow more sensitive, the conversation will only deepen, uncovering connections we've yet to dream of. The cosmos speaks in many tongues. Finally, we're learning to listen to them all. Black holes might seem eternal, but even these cosmic titans could have an expiration date, one that gravitational waves are uniquely equipped to uncover. According to Stephen Hawking's revolutionary theory, black holes aren't entirely black. They emit faint radiation, slowly leaking energy until they vanish in a final, explosive whisper. This process, known as Hawking radiation, would take longer than the current age of the universe for a typical black hole, but gravitational waves could offer indirect clues about how it unfolds, or even reveal alternative endings we've yet to imagine. Picture a solitary black hole drifting through the void. Over unimaginable eons, quantum effects near its event horizon cause particle-antiparticle pairs to form. Normally, they'd annihilate instantly, but if one particle falls into the black hole while the other escapes, the whole loses mass. The smaller the black hole, the faster this evaporation accelerates. For a stellar mass black hole, the finale would be spectacular. A burst of high-energy particles and potentially a gravitational wave pop as the last remnants collapse. But here's the catch, we've never observed this. The signals would be incredibly faint, swamped by the universe's background noise. That's where gravitational wave astronomy gets creative. Instead of waiting for single black holes to evaporate, scientists are hunting for anomalies in mergers that might hint at evaporation's effects. Imagine two black holes spiraling toward collision. If Hawking radiation has subtly altered their masses or spins over their lifetimes, those changes could imprint on the gravitational wave signal. The waveforms might deviate slightly from Einstein's predictions, especially in the high-frequency, ring-down phase where quantum gravity effects could become noticeable. Future detectors like the Einstein telescope, with its razor-sharp precision, might catch these whispers, but evaporation isn't the only possible endgame. Some theories suggest black holes could tunnel into white holes, hypothetical objects that spew out everything they've ever consumed. If this happens, the transition might produce a distinctive gravitational wave burst, a sharp crescendo unlike any merger signal. Others propose that black holes could leave behind stable remnants, dark, ultra-dense fossils that still warp spacetime but lack event horizons. These relics might vibrate at unique frequencies, emitting continuous gravitational waves that next-generation observatories could trace back to their origins. Then there's the wild card, primordial black holes. These hypothetical objects forged in the Big Bang's chaos could be tiny enough to evaporate within human timescales. If they exist, their death throes might unleash gravitational waves at frequencies too high for current detectors, but not for future quantum sensors or resonant mass experiments. Some researchers even speculate that these explosions could produce cyclical bangs, birthing new universes in their wake. Gravitational waves might carry echoes of those cosmic rebirths, encoded in their polarization or timing. The search isn't just about physics, it's about philosophy. If black holes truly vanish, what happens to the information they swallowed? Does it leak back into the universe via Hawking radiation, or is it lost forever? Gravitational waves could tip the scales in this decades-old debate. A single detection of an anomalous ring-down or an evaporating black hole's final burst would rewrite our understanding of entropy, quantum mechanics, and the fate of information itself. For now, these ideas lie at the edge of theory and observation. But with every upgrade to gravitational wave detectors, we edge closer to answering one of cosmology's ultimate questions. When the universe grows cold and dark, will black holes be the last things to go, or will they fade quietly into the night, leaving behind only ripples in space-time to mark their passing? From the first tremors of colliding black holes to the haunting whispers of the cosmic microwave background, gravitational waves have rewritten the rules of astronomy in just a handful of years. These 30 discoveries aren't just footnotes in a textbook, they're seismic shifts in how we perceive the universe. We've decoded mergers that forge gold in neutron star cataclysms, caught glimpses of black holes spinning spacetime into knots, and even eavesdropped on echoes that might betray the existence of wormholes. Each ripple in spacetime has peeled back another layer of cosmic mystery, revealing a universe far more dynamic, violent, and interconnected than we ever imagined. Think about where we stood just decades ago. Black holes were theoretical oddities, dark matter was a placeholder in equations, and the Big Bang's first moments were pure speculation. Today, gravitational wave observatories function like cosmic stethoscopes, letting us listen to the heartbeat of collapsing stars, the death cries of primordial black holes, and the faint tremors of quantum foam itself. We've confirmed Einstein's wildest predictions while stumbling upon phenomena his equations never anticipated, like intermediate mass black holes that defy stellar evolution, or neutron star quakes that expose the strange physics of matter crushed beyond recognition. But the most thrilling realization, this is just the opening act. Every unanswered question, whether dark matter leaves fingerprints on black hole collisions, if quantum gravity imprints on spacetime's vibrations, or how supermassive black holes find each other across galactic distances, is a puzzle waiting to be solved by the next generation of detectors. The Einstein telescope, LISA, and Cosmic Explorer won't just refine our knowledge, they'll unveil entirely new chapters in this story. Imagine mapping the universe not by light, but by the gravitational echoes of its birth. So stay curious, the cosmos is humming with secrets, and gravitational waves are our newest cipher. Hit subscribe to journey with us as we decode the next groundbreaking discovery, because the universe isn't done surprising us. When the next ripple arrives, you'll want front row seats to the revolution.